Imagine training a robot to perform a delicate kitchen task in a pristine simulation. It succeeds 96% of the time. Then you take it outside, or even just turn on a slightly dirty camera lens, and it completely fails. This isn't a bug. It's a fundamental vulnerability in how modern vision language action models process visual information. Today, we're breaking down StableVLA, a new architectural approach that injects intrinsic robustness directly into the model's backbone, achieving state-of-the-art performance under severe visual corruption without a single extra training image. Let's set the stage. Vision language action models, or VLAs, have rapidly become the standard for embodied AI. They take a camera feed and a text instruction, align them through a frozen vision encoder and a language model, and output robot actions. The bridge between the vision encoder and the LLM is typically a lightweight adapter or projector, often just a multi-layer perceptron. In clean benchmarks, this works beautifully. But real-world environments are noisy. Sensor artifacts, motion blur, fog, or even physical obstructions like oil on a lens introduce perturbations that simply weren't in the training data. The current fix for this is brute force. Flood the training set with augmented noise or run domain randomization in simulation. But that's computationally expensive, and it teaches the model to memorize specific noise patterns rather than learn invariant features. It hits a hard ceiling when faced with unseen disturbances. The authors of StableVLA asked a sharper question. What if we don't fight noise with more data, but instead redesign the alignment interface to filter it out intrinsically? Their investigation pinpointed the exact failure mode. When visual corruptions hit the projector, the features degrade catastrophically before they even reach the action policy. Standard MLPs act as all-pass filters. They maximize mutual information indiscriminately, meaning they pass task-relevant semantics and task-irrelevant noise through with equal weight. The solution lies in a decades-old information theoretic framework, the Information Bottleneck principle. At its core, the Information Bottleneck principle forces a model to compress its input representation, while preserving only the information necessary to predict a target variable. Mathematically, you're optimizing an objective that balances compression against relevant information preservation. Now, vision transformers already use spatial self-attention to group pixels into semantic clusters, which inherently aligns with IB optimization under Gaussian assumptions. But here's the critical insight for VLA models: spatial grouping isn't enough. In the output of a vision encoder, semantic signals and sensor noise are heterogeneously distributed across channels. If you only group spatially, you're still propagating noisy channels straight into the LLM. StableVLA shifts the grouping operation to the channel dimension. By treating each channel as an independent information unit, the model can identify robust semantic subspaces and suppress uncorrelated noise before it contaminates the policy. This theoretical shift gives us the IB adapter. Let's walk through the mechanics. The input features are partitioned into multiple heads. For each head, the model computes a query, a key, and a value. Crucially, the key is an identity mapping of the input features. This preserves the original geometric structure and high-frequency spatial cues that get flattened by redundant projections. The filtering happens when they compute the Gram matrix, which captures the covariance between every pair of channels across all spatial tokens. This covariance map tells us which channels move together semantically and which are just random noise. To turn this covariance into a filter, they apply a learnable sigmoid gating function. This is a deliberate architectural choice backed by theory. They assume an independent Bernoulli latent structure for the channels. Unlike softmax, which forces channels to compete in a categorical distribution, sigmoid allows independent channel suppression. A noisy channel will have low covariance with semantic-bearing channels, driving its gate value towards 0, while robust channels stay open. The filtered features are then passed through a nonlinear transformation and reconstructed by modulating the value tokens with this spectral gate. The result is a compressed, noise-resistant representation that satisfies the IB compression objective before hitting the LLM. But filtering channels isn't free. Robust semantic grouping can sometimes attenuate the high-frequency spatial details that precise robotic manipulation requires. To solve this trade-off, the authors introduce the fused IB adapter. It's a dual-pathway design. One branch is a standard MLP that preserves raw, high-fidelity spatial details. The other is the IB adapter that extracts covariance-filtered semantic features. These two are fused with a tunable coefficient, and during training, they apply stochastic pathway dropout. This means the model learns to rely on the robust IB pathway when tasks demand long-horizon semantic planning, but can be forced to retain the high-fidelity MLP pathway for fine-grained pick-and-place operations. It's a highly flexible, task-aware architecture that doesn't sacrifice precision for robustness. So does it work? The empirical results are striking. On the Libero and CALVIN benchmarks, StableVLA consistently outperforms the baseline VLA adapter across all corruption severities, with average performance gains of over 30% under severe noise, blur, and weather conditions. More impressively, it achieves this with a 500 million parameter backbone, completely bypassing large-scale pre-training on datasets like OpenX embodiment. It matches or exceeds the robustness of 7 billion parameter foundation models that were trained on massive embodied datasets. But benchmarks are just the first step. The team deployed StableVLA on a physical dual-arm robot and introduced real-world visual corruptions, digital noise and blur, plus physical obstructions like oil smears and plastic lens covers. Where the baselines suffered catastrophic success rate drops, StableVLA maintained manipulation capability, proving that architectural inductive biases can genuinely close the sim-to-real gap. StableVLA demonstrates that we don't always need more data to solve real-world generalization. Sometimes we just need better information flow. By reframing modality alignment as an information bottleneck problem and enforcing channel-wise covariance filtering, the researchers have built a lightweight, parameter-efficient adapter that intrinsically suppresses visual noise. This isn't just a marginal improvement. It's a shift in how we design the interface between perception and action in embodied AI. As we push VLAs into unstructured, real-world environments, architectures that prioritize intrinsic robustness over brute force scaling will be the difference between a lab prototype and a reliable robot. If you want to dive into the full mathematical derivations, ablation studies, and deployment details, I've linked the paper and code in the description. Thanks for watching, and keep pushing the boundaries of what these models can actually do in the wild.